the hydrocarbons. Remember, it's only looking at carbon and hydrogen compounds, and we talked about the different classes. So this should have been done in Intro to Organic, where we have the alkanes, alkenes, alkynes, and the aromatics. Right? For us, we're going to focus a lot today on the alkanes, do some review of some of the naming, and then look at how do we look at more of the stereochemistry of alkanes around that single bond. Alright, so the general formula for alkanes is the CnH2n plus 2, so we're just multiplying the number of carbons by 2, add 2. Alright, so that we get it moving. Most of our alkanes are our sort of energy sources. So whether we use it for natural gas or petroleum or coal, our alkanes are in that sort of branch of compounds. And it's important to know, the reason I like when we talk about where we find these molecules is because when you connect what these structures look like with what those compounds do, it sort of gets you more thinking about, you remember them better, but you also think about what could I do to manipulate those structures, right? And how could the manipulation of the structure change the properties, right? So for the only thing that alkanes are really good for is to burn it, all right? So just looking at some of the smaller alkanes will have lower boiling points. And we talked about last week, remember last week we talked about why the shorter alkanes have lower boiling points, right? We talked about the van der Waals forces, the dipole-dipole interactions. So we just want to make sure we remember those things that affect the properties, right? So just an example here, the shorter the alkane, the lower the boiling point. So methane boils at negative 160 degrees, so that means at room temp, what is its state of matter at room temp? Methane. If it boils, so what happens when something boils? What does it go from? Liquid to gas, right? So if it boils at negative 160, what is its state of matter at room temperature? Gas, right? It's a gas. All of these are gases, right? You know they're gases because their boiling points are lower than the room temperature, right? And so for you to get liquid methane, you have to sort of get it down to negative 160, right? But another way how we get liquid, so we have liquid butane and liquid propane, that is because of the pressurized system, right? So you can sort of affect the boiling point by affecting the pressure. So you all remember Gen Chem 1, Gen Chem 2, where we talked about why I'm going to bring it up. PV equals nRT, pressure, volume, temperature. Alright, so just some examples of some alkanes. Again, based on the length of chain, we have different names. The assignment that you all did on Moodle, not on Moodle, on Achieve, was sort of giving you a review practice of those alkane naming. Just know some of the isomer names that we'll use are like isopentane, isobutane, isopentane, right? So neopentane, so these are just some of the different isomer groups that we have common names for, alright? Alright, so let's talk about some of these small alkanes, right? And we're going to focus first on butane and some of the isomer names, right? So butane has 4 different isomers, not 4 different isomers, it has 3 different isomers, so we have 2 different, what am I talking about? 2 different isomers. It's the butyl groups that have 4 different isomers. So we have isobutane, which has the connection of the carbons in a T shape. So easier regular N-butane is just a straight chain isomer, right? Now, the difference between what types of isomers are these? So we have two main categories of isomers we talked about, right? And we talked about this last week, I think. Geometric isomers and constitutional isomers, right? Geometric isomers are where we have difference in orientation. So this is where we have stereochemistry, right? Which we'll talk a lot about today. Then, constitutional isomers is where we have the connections different. Alright, so what kind of isomers are these? Constitutional or geometric? They're constitutional isomers. Not geometric because constitutional has to do with they're connected differently. See, N-butane, all those carbons are connected sequentially, so in the same order. So 1, 2, 3, 4. But when we have a constitutional isomer, we have connected it differently. So now we have a different connection. So instead of it being connected consecutively, we now connect it in like this T form, right? So if I move my constitutional isomer, it's just different, right? It's different in terms of the connections. Alright. Then we have the pentane. So we have 3 different versions of pentane. So the first one is our N-pentane, right? Which is the regular pentane, straight chain pentane. But then we have isopentane and neopentane. And I want us to remember these names because we're going to use these common names when we start sort of combining these molecules together. Alright, so isopentane and neopentane. Isopentanes, and these are what type of isomers again? Constitutional, right? Constitutional isomers. Okay. Again, this is just review. Alright, so that's why we're kind of moving through this quickly because I want to get to the more important stuff. Not more important, but just the more relevant stuff to this organic compost. Right? So now just looking at, again, review. Whenever we name an alkane, we use the ANE suffix, right? And the prefix comes from the number of carbons. If you didn't know what IUPAC stood for, it was the International Union of Pure and Applied Chemistry. There are a bunch of chemists in this, right? Annoying little group of Europeans that just decide how to name stuff like, and it's so dumb. Anyways, they get a position and a title and they come up with the universal way of sort of identifying how to name stuff. Now, they are important because when you publish something, you want to make sure you're able to standardize the naming system, but at the same time, they contradict themselves sometimes. Sometimes some people agree with the older version versus the new version. It's just so annoying. Alright, but just looking at some of the rules that we use is that we first will always find the longest carbon chain. Right? That's sort of standard. And then from there we do the numbering based on where the nearest substituent or where the nearest functional group is, right? And then we assign the names for each of the alkyl groups, or if we have halogens or whatever, we assign the name, right? So for straight chains, just so that we remember, the numbering system is from left to right or right to left. So we can do 1, 2, 3, 4, or 1, 2, 3. So that, again, is just review, right? This is just review that we've done, right? So if we look at this example here, it would be 3-methylhexane, right? We look for the longest chain being 6 carbons, and then because on this longest, because remember, if we count from here, this is only 5 carbons across, right? So we have to include this little branch to indicate 6 carbons. So that's why carbon 3 will have our methyl B. Alright? We have some other examples here where you can look at the number of carbon right? So this is a 7 carbon chain, and this is also a 7 carbon chain. But notice the difference between which 7 carbon chain they used, right? Naming has to be simple. So we always pick the more simplified version, right? So if you look at those two, the name of this substituent is more complicated than naming these other substituents. You all see that? Like, the name of this substituent would be isopropyl, right? 3 carbons and an isobutane. But why have to go into all of that extra complicated naming when you could have just done 7 carbons this way, and then these groups that are attached, ethyl and methyl groups, a lot more simple than this, right? Alright, let me ask you real quick, if you don't name the one on the right side in your notes, just quickly, just as practice, right? Name the chain on the right, right? Name it on the right. So put the number, everything.
Put 3 ethyl, 2, 4, 5 methyl again. That one? Or the next one? That one? That should be different.
Alright, so let's start with the name. So what is the parent name that we have?
Heptane.
Heptane, right? So heptane is the parent name. Right? So heptane is our parent name, right? And then in front of that now are our substituents. So where did you all start numbering? From the bottom up or from the top down? Bottom up. Because if you look, let's see, 1, 2, 3, 4, 5. So let's draw it. So it looks like we have to do it, right? So let's do it. This is
Which one we doing?
I hope you all didn't use Google to do your assignment because
Yeah, we do this one.
Alright, so we have our substituents here, right? So everything else is our long chain. So if we number it from top down, right, what we get here is 1, 2, 3, 4, 5, 6, 7, right? So what happens is we get a group at carbon 3, a group at carbon 4, a group at carbon 5, a group at carbon 6. Alright? So that's where our groups are. So we have a group at carbon 3, 4, 5, and 6. If we number in the opposite direction now, I get 1, 2, 3, 4, 5, 6, 7. So what happens is we have a group now at carbon 2, a group at carbon 3, a group at carbon 4, and a group at carbon 5. Between these two, which is the lower set of numbers? The bottom. So remember, you number based on lowest locations. Alright? Lowest locations. So now that we have the correct numbering system, then we go ahead and name it. So we have 3 groups that are methyl groups. So we combine that name as a tri-methyl. Alright? So remember, we do it like that. Right, trimethyl, and I say remember because this was I'm teaching this in Intro to Organics, so you all should know this already.
Yes.
And then this group is just the ethyl group, right? So when we name it based on alphabetical order. So we'll start naming which one of these do we name first? Ethyl. And what location is our ethyl group? Carbon what? 3. So 3 ethyl, and then we give our locations of the rest of our methyl groups. So our methyl groups are on carbon 2, 4, 5, and then it's trimethyl heptane. Well, it's a good thing I made you all do this. Alright. That's why we do a review, right? We do a review. Any questions on this part? No? Alright? Straightforward. So remember, with the naming for the alkanes, it's going to be the same for the alkenes and the alkynes. The only difference with alkenes and alkynes, the numbering will just start with the double bond is closest to. Right? So that's the only difference. But same thing. And we could do some examples next. Alright? Alright, so now let's talk about some of the groups that are attached that have like different names. So some of the common groups, alkyl groups that we have, remember alkyl groups and the carbon and hydrogens. Some of the common ones we have are methyl groups, ethyl groups. We also get this a lot in isopropyl. Right? It has 2 carbons, right, representing a propyl group. So the isopropyl group is a common one, and then the butyl groups has 4 different groups, right? So we have the isobutyl, and I like to draw it. So the isobutyl, right? So if I have a carbon chain like this, right, I can have an isobutyl group. So we have 4 different groups that we'll see. This group, and this group. Alright? So these are the 4 different types of isomers of the butyl group, right? The reason we need to know these names is these are common names that we see a lot, right? So we want to name it the correct way. So we don't name it as like butyl, right? We have to give the name to the specific group. So this group right here is the sec butyl, right? Sec butyl because it has 1, 2, 3, 4, and it's sort of an uneven sort of distribution of the 4 carbons, right? This group down here, the chicken foot, is the ter-butyl, right? So you have a ter-butyl, which is our chicken foot like that, right? Easy to remember that one, looks like a chicken foot, right? This one looks more like a T-bone steak, so I call this the isobutyl, right? So isobutyl, looking like, so what happens is the 4 carbons are this carbon here, and then these 2 that have like this Y, right? So you get a Y or T-bone steak for our isobutyl, ter-butyl, chicken foot, sec-butyl, some uneven sort of shape. Alright? So just remember those. I'm sure you all remember the ter-butyl, right? And remember we talked, no, I'm not going to say remember, I'm teaching them in class. You all are new students, I don't know you. First time I'm ever having you all in class. Okay. Alright. So, go ahead. So the isopropyl group is different because the propyl group has all sort of combined. So let me draw down this example right here. So a propyl group has 1, 2, 3 carbons, right? So it's 3 carbons in this form. Isopropyl group is where you create this sort of Y. So I'll show you. So this is our propyl group. This is our isopropyl. So this has 1, 2, 3 carbons. Here we have 1, 2, 3 carbons. So they look like 2 different substituents. So that's why we have to name this isopropyl. And then this one is just the propyl group. Alright? So just so that we understand the difference. The butyl groups has 4 carbons. So if you notice, 1, 2, 3, 4. Here, 1, 2, 3, 4. Here, 1, 2, 4. This one is a little tricky because sometimes this isobutyl sometimes tricks me too, right? Between the isobutyl and the isopropyl. Right? And you have to just look at how many carbons are numbered. So with this one, if this was a long chain, say for example, the long chain was like here, right? You'll notice that the isobutyl group has an extension and then the isobutyl group starts, right? So that's the difference between here where it's directly attached. And it just practice seeing them and knowing the difference between the two. Right? Any other questions about the common names for isomers? I like these slides, there's so much more. It feels like I'm teaching on the level organic chemistry. Last semester I felt I was just teaching like almost graduate level. So I had to find some slides that were a lot more straightforward. Alright. Alright, so we don't need to talk about we did practice rules. Alright. So I want you all to go ahead in your notes, just draw the structures of these two. So notice we're using the common names. So I want you all to just draw them. Use the complete structural formula. So don't use this skeletal formula to draw them, right? I want you all to draw it using the complete structural formula with the carbons and the hydrogens. Alright, so those two names right there, I want you all to do that.
person for the for those ones right, the 4 and the 5 where the group will be right, and then we got the 10 and then the kid for 10 and 8, right, and then the ISO winning 3 and the next one 4, right.
It's not the ISO the two, it's based on the pro person. So youth representing 4, pro representing 2. So ISO and T, the terror just represents what kind of ISO. Alright, so let's look and see the structures if you don't have the correct structures. So you have the 4 isopropyl, so on carbon 4, you have the isopropyl group, and then the octane representing 8 carbons. Then the 5 terbutyl, so you have 10 benzene, and then on the carbon 5 you have the right? Question? Like 8 carbons. So this supposed to have 10. Alright. So let's do one more. So go ahead and draw this and then give the name. Alright, so one more drawing.
By Tulun. Tulun. How much you count? 9? 9? 7? Yeah. I'm gonna count it at first. Because the pieces, right? That's it. From the pieces from that side, right? Go this side, go down, shrink, then down. That's it. But then if you count this side, I'm going down, that's 7. Because the itu the like number 2. Yeah, 7. I don't know. 2 itu 5 betul. Yeah, 5 for that one. The last one.
If you can have Brave Soul come to the board and name this, show me the longest chain, identify the substitute and so forth. Anybody want to come and try?
Try. Mine, come hold this round. I don't know.
So circle the longest chain. So let's get our first one down. Alright, does everybody agree with Joseph's longest chain? No. Agree? No. Why? When is there a longer chain?
On this side?
But then count it.
Yeah, this one is it.
Right.
Okay.
So we just do this one.
Because of the ethyl group.
Yeah, but so that part is only if we have the same number of the chains. So because they have two different numbers, then we just go with the longest one. Alright.
Gambar? Oh, the isoprop.
Alright, Joseph, thanks for starting us off. So we had the longest chain, right? Octave. So the rules, like I said, the rules for when to name it, right? We start with the longest chain. Then the next rule is numbering it. So where did your number from? Down, up, or up, down? Down, up, right? So 1, 2, 3, 4, 5, 6, 7, 8, right? So we do the numbering down, up. So we have the correct numbers, 2-dimethyl. Now, what happens is when we look at the substituents, right? Notice we have 4 of the exact same substituent. So because there are 4 of the exact same, we combine them all into one name. So we'll combine all 4 of these as tetramethyl. Right?
Yeah.
Tetramethyl. Alright? So that we can combine all 4 of them into one name. Alright? So that's why we have the combination. The next thing is because we have 4 methyl groups, we have to give locations for all 4 methyl groups. So the first location is carbon 2. But at carbon 2, we have 2 methyl groups there. So we have to indicate it as a 2, 2 for the 2 methyl groups. Then at carbon 3, we have a methyl group, and at carbon 6, we have a methyl group. So that's the 2, 2, 3, 6 tetramethyl. So that's how we would combine all 4 of those together, right? Alright, this is correct. We have the 4-isopropyl. Remember, there's a dash between the, well, no, for isopropyl, we don't need the dash. So 4-isopropyl. So from there, remember we do the, so which one will come first in the name? The tetramethyl or the 4-isopropyl?
The iso.
Tetramethyl. Right? Tetramethyl comes first because you do the alphabetical order on the M, not the T. Alright, so we do it on the M, not the T. Just like we do it on the P, not the I. Alright, so how we name this is 2, 2, 3, 6 tetramethyl 4-isopropyl octane. Alright? Everybody got our part? Yep. So for some reason they put the tetramethyl after the isopropyl. I don't know if this was a mistake because unless they come in the I as alphabetical order, but from my understanding it would give the P. I did it wrong. Alright. So boiling point to alkanes, just so that we review again. When we have larger surface areas, more van der Waals forces, and then we tend to have larger, higher boiling points. This is, again, if we have some branches, like the isogroups, then we end up with a slightly lower boiling point than the straight chain alkanes, right? And notice it's sort of in a nice increasing curve. So as we increase in number of carbons, we also increase in boiling point, right? So that's how we get different groups, right? Melting points, we kind of have similar trends. The only difference is that in these trends, the difference between odd and even number of carbons tends to give a different melting point. So for example, an even number 6 carbon chain will have almost the exact same melting point as an odd number 7 carbon chain, right? And that has more to do with symmetry of the compound. So with odd number alkanes, you tend to have like a more symmetric compound because you have one in the middle and then the flanking sides are even, right? So odd number alkanes tend to have a slightly lower boiling point, melting point, I mean, because of that sort of symmetry, uneven symmetry, right? So even numbers tend to pack easier, better together, and odd numbers have this branch alkanes will have higher melting points than the unbranched, right? So it takes more energy to melt, right? A branched alkane than an unbranched. Alright, so when we did lab for Orbital 1, we did cracking or hydrocracking of alkanes. This is one of the first sort of reactions that we see with alkanes is when we can crack the alkanes or break up the long chain alkane to get our short chain alkanes. And this is how we get things like gasoline and kerosene and so forth, right? So I think I mentioned before that gasoline is made up of 8 carbons, right? But it's an isooctane, so it's 8 carbons in branches. But with gasoline that comes from petroleum, when you burn petroleum or heat petroleum with this catalyst, you then break up the long chain petroleum compound. So the petroleum compound is usually like 20, 22 carbons or something like that. And then you break it up, you sort of chop it up, and that gives you different versions of alkane. And I don't know if I mentioned this here, but when they first refined petroleum, right? When they first came up with the technique for cracking alkanes, they used to throw away gasoline. So gasoline was a byproduct to them. So they would dump gasoline in the rivers. So because at the time, when they found oil, the useful part of the oil was to light lamps. So they used to light kerosene lamps. So they cared more about selling you kerosene and cared less about selling you gasoline, because gasoline at the time didn't have the combustion engines that we have today. So what they did is, again, it's whatever the purpose is. So if I value kerosene over gasoline, kerosene used to cost a lot more at the time because they used to have their lights, their lamps, and so forth. So they used to have kerosene fridges and so forth, right? So then gasoline used to be burned or just dumped in the river. Right? Now we're trying to collect as much gasoline as we can. I literally reciprocity gas tank to make sure we have it. So it's just interesting to see how things change. But either way, we can have the catalytic version of it, whether we're using hydrogen or we're using just heat. In the lab, we did it with the boiling chips. So that's where you got the cracking of the algae. Alright, just reviewing again the different versions or structures of our methane, ethane, propane. For the carbon and hydrogen bonds we talked about last week, where hybridization of those bonds gives us the sp3 version, right? And because we have sp3 carbons, we have 109.5 degree angles, right? And that angle is just the furthest they get away from each other. But we have different representations. We use the ball and stick model or the space filling model. For ethane, this is where we look at in this version here, this ball and stick model, we're going to look at the conformers, right? That can exist as this single bond rotates, right? So that's one of the things we were talking about. Again, you have two sp3 carbons, so you still have the 109.5 and the 109.5 in all directions, right? These lengths of the carbon bond. So notice, and this is something important, right? Notice the difference in length of the bond between the two carbons and the bond between the carbon and hydrogen, right? The carbon bonds are longer than the carbon-hydrogen bonds. Why is that so? Why are the bonds between carbon longer than the bond between carbon and hydrogen? Because we talked about this last week. Y'all can give me wrong answers. Wrong answers are welcome. Any wrong answers anybody want to throw out? Why do we have longer carbon bonds and we have carbon hydrogen bonds? What's the difference?
The dipole bond.
What does the dipole have to do? Difference in electronegativity, right? Difference in electronegativity. Now remember, electronegativity, what it does, it causes an atom to pull electrons towards itself, right? So with two carbons, there's no difference in electronegativity. So either carbon is sort of going to be pulling electrons away from each other. So it stretches the bond, right? But when you have a carbon and hydrogen, carbon has a higher electronegativity than hydrogen. So what it does, it pulls the hydrogen towards itself, right? So the carbon bond is sort of stretching itself. Carbon-hydrogen bond are pulling it towards itself. So what happens is you end up with a shorter carbon-hydrogen because the carbon has a higher electronegativity than the hydrogen, pulling the electrons towards itself, making the bond shorter. Right? So that's why it's important for us to indicate these differences. And it seems like a small difference, like 0.45 angstroms. That seems like nothing, right? But it is significant when we talk about the hydrogens and carbons, how we go ahead and do those sort of drawing of our molecules, right? Alright. Other thing we have to understand, and what we'll talk about hopefully today, right, in the last 15 minutes, well maybe not, but we're going to talk about the conformations, right? So because the carbon-carbon bond is a single bond, we can rotate around that axis, and then we get a different rotation above the single bond. Alright? So there are different rotations, right? So, it would have been nice for me to have them over here to show you all, but you all just have to take these words for it. Alright? So what you notice is that because this sp3 single bond allows for rotation, you could get a conformer that looks different. So what you see is that right now, this hydrogen is on top of the molecule, right? And then you switch it around where the hydrogen is on the bottom, and these two hydrogens are sort of split in between. Right? So we're going to get different possible conformations, and different possible conformations give us different energies of these molecules. Right? And that's what we do. All right. I'm going to ask you a question, but I'm not sure. I guess we'll talk about it when we talk about energies. Alright, so first let's look at changing this model into a more two-dimensional plane. Alright? So this is a Newman projection. So a Newman projection is where we try to judge the stability of the different conformers, right? So notice in the back, so what you do is the back carbon represents that circle. Alright, so and I guess this would be this. Alright, so the back carbon, so let's look and see what we're talking about. So I have this carbon and single bond. So I have, in this example, we have a hydrogen here. What does the dash mean, guys? When I draw a dash, at the back and then a wedge at the front, right? And then this one, and then dash here. Alright, so what we see in here is that this hydrogen is to the back, this hydrogen is to the front. So we have this sort of anyway, my fingers kind of, anyways. So we have this sort of seesaw looking thing to the hydrogens on the back. In this one, the hydrogens on opposite sides that are in the plane, and then this hydrogen is to the back there, this one is to the front. So now we want to draw the conformer. So what we do is, we take, so we're going to look at it from this direction. So we're looking, our eyes are looking from this direction, right? So this front carbon, right? This is my front carbon. Because I'm looking this way, and this is my back carbon, right? So this is carbon 1, carbon 2, all right? So when I look at it down this bond, right? This carbon on the back we draw as the circle, right? So carbon 2 on the back is drawn as a circle to represent the back of the molecule, right? Now if I look at this circle, right, if I'm looking at it down this way, this hydrogen, will it be on the left or the right? Let's look at it, we're looking at this carbon here, right? So right now this hydrogen is to the back, this hydrogen is to the front. So where would this hydrogen be, on the left or the right? On the left, right? Because it's drawn to the back, right? And then this hydrogen on this side is to the right. And then where we put this hydrogen? Down, right? Alright, for those of y'all that didn't see what they just did, right? Alright, so I'm looking at this carbon right here, right? On the back of it is a hydrogen, on the front of it is a hydrogen, and down is a hydrogen, right? When I turn this way, my carbon, that hydrogen that was on the back now moves to the left, the hydrogen that's on the front now moves to the right, and then this hydrogen stays down, right? So now let's draw the front of our molecule. So the front of the molecule now represents the carbon that's like in front of you, right? So this carbon, where does this hydrogen exist? On the top. So this hydrogen is here. So this is carbon 1 in front. So this hydrogen is on the top. What about this hydrogen? Left or right? On the what? This hydrogen to the back. When I turn it this way, what happens? This hydrogen is on the left, and then this hydrogen is on the right, right? Your brain has to sort of like look at it and see. So you're looking at it like this, and then you turn it this way, all right? So you're looking at it like this. So imagine, no. All right, so this is like, say for example, like this is, the top of my head is a hydrogen. This left foot is a hydrogen, and this right foot is a hydrogen, right? So I'm looking like this. When I turn this way, the top of my head is a hydrogen. This left foot is on the left side. This right foot is on the right side, right? So that's the best way for you all to sort of look at it. All right. Again, these Newman projections are sort of getting your brain to think or look at stuff more geometrically, right? So, all right. Now the reason it's important for us to draw this is because I can rotate these hydrogens around, right? So I can take this carbon and I can rotate the hydrogen. So what happens is if I rotate it, it's going to give me a different conformer. So that's where we talk about conformation. So let's look and see what happens when we rotate our bonds, right? So now, again, we are looking at where the circle is the back. And we don't move the, well, for this one, it looks like they're moving both of them. Oh no, they're keeping it back the same. So I'm going to draw it like how they have it so you all can kind of see. So on their back carbon, right, and I'll put their back carbon, right? So on their back carbon, they have a hydrogen up, they have a hydrogen to this side, and a hydrogen to this side. How would we draw this differently if this is the back carbon? What would look differently here? Think about it. Where would we put a hydrogen first? If this is our back carbon, where does the first hydrogen go? On the top. Right here. And then where is this hydrogen? Bottom of dash or wedge? Dash, right? Because this hydrogen, because it's back, we turn it this way so that this hydrogen goes in the back, and this hydrogen comes to the front. Alright? So that's how we change it. So you all have to learn how to convert from the Newman projection to the structure and from the structure to the Newman projection. Right? So we have this. Now the front carbon that they have here is where we take a hydrogen here, a hydrogen here, and a hydrogen here. Alright, and this is our eclipse model. Alright, do we have to change anything of this carbon to reflect this one? No, because if you look at this, the hydrogen is already on top. This hydrogen to the left is on this side, and this hydrogen. So what you notice is with this conformer, this is called the eclipse conformer. Because we can't draw it exactly on the line, but if you actually look at it, it is exactly on the line, right? And the eclipse conformer, what happens, what do you see is happening up here? What's happening at these three hydrogens? They're not just mirrored, they're like close to one another. So because they're close to each other, what's happening is there's going to be some conflict, right? Some conflict, right? Some energy sort of repulsion, right? So what's happening is that at each of these hydrogens, there's some sort of interaction that is creating an energy barrier, all right? So what happens is in our eclipse conformer, which is this first one here, the energy is higher than when we stagger it. So when I stagger it and I rotate this down, so I take this and I rotate this 6 degrees, alright, we create this staggering. And the staggering allows for a lower potential energy. Then when I rotate it again, I go back up to high energy and rotate it again another 180 degrees. So what happens is each rotation, we're taking this and rotate it 60 degrees to here, right? Then we rotate it again, 60 degrees to here. And then we rotate it one more time, 60 degrees to here. So what happens is that each of these rotations, we get a different energy, all right? So first, this is our highest energy. When we rotate it 60 degrees, now we get our staggered conformation that lowers our potential energy, right? Then we rotate it another 60 degrees, so the combination of 60 plus 60 is our 120. So this is the 120 degree angle. So the 120 degree angle gives us another eclipse position, right? Then when we go from another 60 degrees, which is our 180 degree angle, we then get another stagger, and that's how we get different energy conformations. Alright, any questions? Staggered is the most stable, lowest energy. Yep. Any questions? Yes, no? Maybe so, yes. I think I don't know if it was posted on Achievers yet. I think if I didn't post on Achieve, I'll post it this week. So probably by Friday, you should have a quiz. By Wednesday, a quiz will be ready, and then it will probably be due over the weekend. Any other questions? I hope you can understand this part.
Hopefully.
Tell me the difference. No, like, I'm trying to explain it, right? It's like you're getting close to one another. Alright, so I will see you all